Okay, so the last video cut me off at the 15-minute mark, but in the middle of this example 3.3, we are looking at using the method of components to add three vectors. And so what we had done so far is we had sketched out a diagram here of our three vectors, 620 kilometers east, 440 kilometers at an angle 45 degrees south of east, and then 550 kilometers at an angle of 53 degrees south of west. So what we need to do is break each of them down into their x and y components. The first one is really easy because it's already horizontal, so it's all x, 620, and no y component. The second one we broke down into its x and y components by taking the magnitude of the vector multiplied by cosine of the angle, 45 degrees, to get 311 kilometers, and that's positive because it's going right. And the y component is 440 kilometers multiplied by sine of 45, which still gives us 311 kilometers, but since it's going down, it's a negative 311. So the last thing we need to do, or rather the next thing we need to do, is take our third component, or our third vector, d3, and multiply, find its x component by taking its magnitude, 550, and multiplying it by cosine of the angle with respect to the x-axis, which is 53 degrees. And we need to find the y component of this vector by taking its magnitude multiplied by sine of 53 degrees. And so in the x direction, it is going to the left, which makes it negative. So this is negative 331 kilometers. So 331, and don't forget that negative sign. And in the y direction, it's still going down, so that's also negative. So it's negative 439 kilometers. So I'll put that into my table as well, negative 439. What we need to do now is sum the x components and sum the y components in order to find the x and y components of the resultant. So 620 plus 311 minus 331 gives us positive 600 kilometers in the x direction, and 0 minus 311 minus 439 gives us negative 750 kilometers. So these are the x and y components of the resultant. And as I advance the slide, you can see these same results in a nice, neater table here. So what we need to do now, we have found that the resultant is going to be 600 kilometers in the positive x direction and 750 in the negative y direction. So basically this creates a right triangle, and we want to know what is this angle and what is the magnitude of the resultant. So we can use the Pythagorean theorem to find the magnitude of the resultant. dr is going to equal the square root of the other two sides squared. So the square root of 600 squared plus 750 squared. And that equals 960 kilometers. But we also need to find the angle. So the angle is equal to the inverse tangent of the opposite over adjacent side. So 750 over 600. And that gives us 51 degrees. Now, since the typical convention is to consider the x-axis as being 0 degrees, and positive angles to be up and negative angles to be down or clockwise. We could call this negative 51 degrees. So it's negative 51 degrees. And we might even describe it also like south of east. Okay, and those are the two pieces of information that are needed to fully describe a vector. We need both magnitude and direction. If we don't provide both pieces of information, it's really an incomplete answer. Okay, let's move on to projectile motion. So projectile motion basically refers to the motion of an object that is given some initial force, and as it moves through the air, it is affected by gravity in the y direction. So like the guy shooting a basketball here, he gives the ball an initial force vector. It moves at some angle with respect to horizontal. And what happens is, as the ball travels, it is being affected by gravity. Gravity is accelerating it downward. So the initial upward motion of the ball begins to slow until it reaches the very peak of its arc, at which point the vertical velocity is 0, and then it begins to accelerate more and more in the downward direction. In the horizontal direction, the ball might be slowed somewhat by air resistance, but if we ignore that, then the horizontal velocity of the projectile remains a constant throughout the entire path of the object. So that's a conceptual thing that can be a little hard to understand, is that the vertical motion of a falling object is not affected at all by its horizontal velocity. So if we had a ball on a tabletop, it doesn't matter if we pushed it with a lot of horizontal velocity and caused it to follow this arcing trajectory, or whether it just barely fell off the edge and fell straight down, it would still be falling at the same rate. So it doesn't matter how much horizontal velocity it has, it's still going to accelerate downward due to gravity at the same rate. And here we have some photography showing just that. We have the red ball falling straight down. We have the yellow ball that is given some initial horizontal velocity. Now, assuming that we neglect air resistance, that horizontal velocity will remain constant. But if we just look at the vertical velocity of the two balls, the red and yellow, we can see that they are in fact falling at the exact same rate. So when we analyze projectile motion, we basically need to break it down into two separate problems or two separate issues. We have the horizontal velocity and we have the vertical velocity. The vertical velocity is constantly changing. So if we have this projectile and we launch it initially with this v naught, this initial velocity, that has both a y and x component, over time, over the path of its trajectory, this vertical velocity is going to get smaller and smaller until it is actually 0 at the peak of the path. And then it is going to begin to increase and get larger and larger and larger in the y direction. So the vertical velocity is constantly changing because there's an acceleration present. The acceleration is due to gravity. In the horizontal direction, though, that velocity, that Vx, remains the same. It's the same here, as it is here, as it is here, as it is here, and so on. Throughout the entire trajectory of the object, the horizontal velocity remains the same. So again, we are neglecting air resistance. In the real world, There would be air resistance that would slow it down, but if we ignore that, then we can say that the final horizontal velocity is equal to the initial horizontal velocity. It doesn't change. So in the last chapter, we had 4 constant acceleration equations that we referred back to for several of our problems that we had to solve. And so these 5 equations for projectile motion are very similar. They are very similar to those constant acceleration problems. You'll notice, though, we have an additional equation, and they're separated into these 2 columns. We have to treat horizontal and vertical motion separately because of the way that vertical motion is affected by gravity and horizontal is not. So what these equations tell us, again, is that the final velocity in the x direction is equal to the initial velocity in the x direction. It doesn't change. And the final x position is equal to the initial x position plus the x velocity times time. Okay, so that's just a way to find the location of something along the x-axis. Now, looking at the vertical motion here, we have that the final velocity in the y direction equals the initial velocity minus gt. Notice that because we are specifically dealing with gravity, a has been replaced by g. We also now have a negative sign here because gravity always brings things down. So if gravity, we're going to use gravity as 9.80 meters per second squared. That's what g is, the acceleration due to gravity. So whenever you see this little g, it's 9.8. And the negative sign is already here in the equation. So we don't need to put in a negative 9.8. If we did that, we would be subtracting a negative, and that would be like adding. So we're not doing that. Things don't fall up, they fall down. So the negative sign is already here in the equation. So you just need to plug in 9.8 for g when it comes to gravity. And then these other equations are very similar to the constant acceleration equations from the previous chapter, but instead of x's, we have y's, and instead of a's, we have g's. And again, wherever we have a g, we have the negative sign built in to the equation. So it's minus 1/2 times positive 9.80 times time squared. Okay, so again, this is straight from the textbook, some 7 steps to solving projectile motion problems. Again, read the problem carefully. Make sure that you understand what the problem is asking for. Draw a diagram. It really helps you to visualize what's going on. Set up where you want your origin to be and set up your x and y coordinates. Decide on a time interval. So usually we start at time interval 0. Makes most sense for most problems. And here's a key thing. Examine x and y motions separately. We can't really do both at the same time. You have to do one and then the other. And don't confuse the two. List out what you know and what you don't know. Remember that the horizontal velocity doesn't change, and that at the highest point, the vertical velocity is 0. Then choose which equations you're going to want to use, and you may need to use several in combination. It might not just be as simple as choosing one equation. So in the next video, we'll start looking at a projectile motion example problem, example 3.5.